Good morning, dear students, and once again, welcome back to our course. In the last lecture, we started one of the most important topic from control system that deals with the concept of block diagram, and we discussed in detail about what exactly block diagram is. So, what is block diagram? It is basically a process of representing a system through some graphical technique, and in that technique we try to represent the behavior of a system through some sets of operating block. Sometimes those blocks are also called as functional block, and through those blocks we are trying to define the relationship between the input and the output of the system. Then we discussed with a simple practical example that suppose if you have a series RL circuit, to that we pass some finite amount of current in the form of excitation, and to this it is going to generate some voltage, or it is going to develop some voltage across it in the form of E of t. So what will be the relationship between this E of t with respect to I of t through a block? So here in this case we need to apply some steps. The step number one is, first of all, we need to obtain its corresponding mathematical modeling. Mathematical modeling you may obtain in time domain or you may obtain in frequency domain. But normally we try to obtain mathematical modeling in frequency domain, because ultimately once we have the mathematical modeling of a system in frequency domain, then it is very easy for us to find out the relationship between output and input in terms of frequency domain, which itself define transfer function. And this is what our objective is. Through signal flow graph technique or through block diagram technique, ultimately we want to define or we want to obtain the transfer function of that particular system. And once we have the knowledge about the transfer function of the system, then it is very easy for us to determine the stability or poles and zeros characteristic equation of the system. We are also in a position to define time response analysis and frequency response analysis of that system, and so on. So ultimately, in order to determine the behavior of the system, we should know the parametric function of that system, which is nothing but transfer function. And to determine transfer functions, uh, it may possible that we have the representation of system in, say, signal flow graph or say block diagram concept. So first we convert that into frequency domain, like SL and R. Then small I of t will replace by capital I of S, and then small e of t is replaced by capital E of S. And this will be the output of the system. This will be the input of the system, and this SL followed by R are responsible for the parametric function of the system. So these are going to be the parametric function of the system. That is very important. And then we apply simple Ohm's law to find out the relationship between E of S, I of S. Like E of S is going to be like SL plus R times I of S, and then we define that through a block. So this is called as the block diagram representation for a series RL circuit or a series RL element. Then we discuss some very common terms which are commonly used in block diagram. First one is output. So output indicate the response generated by the block when it is excited by some kind of input. So in this case, E of S indicate the output of the system. Then what is input? Input is nothing but the excitation that we have provided in the form of input to that particular block, so that it is going to generate some desired output. So with respect to our previous case, this I of S indicate the input to the system. So this is going to be the input and this is going to be the output. And whatever the functions which we have written inside the block, this is called as transfer function of that particular block, or you can say the gain of that block or parametric function of that block. Then what is gain of block? So mathematical function or parametric function which is present inside the block is known as its corresponding gain. That is important. So I of s is s plus 1, sorry, s plus r into e of s. So in this case, this sl plus r indicate the gain of the block. And then we find out the relationship between output and input. And what was that? It is simply the product, the like output is going to be equal to input times the gain of the system. This is very important. This is applicable for each and every block. So in this case, output is nothing but E of S, which is going to be equals to input, which is nothing but I of S multiplied by gain of the system, which is SL plus R. So same thing is mentioned over here. Output of the block is going to be equal to input times the gain. Then what is summing point? Summing point is nothing but a point in the block diagram where two or more than two signals either we can add or we can subtract. So this figure indicate summing point. So here in this case, we have three reference signals like R1 of S, R2 of S, and R3 of S. Now, if you see the sense of each signal, R1 of S, R2 of S are additive, whereas R3 of S is subtractive. So output C of S is going to be like R1 of S plus R2 of S minus R3 of S. Then we discussed what is the concept of takeoff point. So takeoff point is a point in a block diagram where we are going to take a signal for feedback purpose. It may be possible that we are going to take the signal for positive feedback. It may possible that we are going to take that signal for negative feedback. So both possibilities are there. But the thing is that the point from where we are going to take the signal for feedback purpose are known as takeoff point. Takeoff point, that is important. Then this figure indicate that through takeoff point we are going to take a feedback signal indicated by symbol B of S for feedback purpose. So this is what the standard representation for feedback signal. B of S always indicate the feedback signal. It may be positive, it may be negative. That depends upon the requirement of the system. But in most of the cases, I told you that we are going to take negative feedback signal. Then forward path, when the flow of signal is from input to output, then it is called as forward path. In the same way, we discussed what is the concept of feedback path. When the flow of signal is in the reverse direction, that means from output to input, then it is called as feedback path. So with respect to this diagram, uh, when the flow of signal is from output to input like this, then this path is called as feedback path. And whatever the signal flowing through this feedback path is called as feedback signal. So this B of S indicate the feedback signal, and this H of S indicate the gain of feedback path. Gain of feedback path. That is important. Where H of S indicate the gain of forward path. Gain of forward path. That is important. Same thing is mentioned over here. G of s indicate forward path gain, H of s indicate the feedback path gain. And then we discussed how to find out the transfer function for a very simple closed loop system. So we apply some sets of mathematical equation. The thing is that while writing these equations, we follow a very simple rule. And the rule is that suppose if we have a block with gain say A, and to that block we applied some input in the form of X, and we are trying to get output in the form of Y. So how this Y, X and A are correlated with each other? It is nothing but output is equals to input times gain. This logic we need to implement to write those mathematical equations. So if we define this in a proper way, then we can write C of s is nothing but E of s times G of s. This will be equation number one. And then at summing point, we can write uh, this E of s is going to be equal to R of s times B of s. And if you combine, say equation 2 and 3, where equation number 3 indicate the relationship between B of s followed by C of s into H of s. This will be equation number 3. So from equation 2, 3, it is very clear that we can write E of s is nothing but R of s minus B of s, but B of s is C of s into H of s. And finally, if you combine equation 1 and 4, we will get this equation as an output. In the last lecture, we had a discussion in detail about these derivations. So C of s by R of s is going to be like G of s upon 1 plus minus G of s into H of s. Now the thing is that in this case, we have taken the nature of the feedback signal as negative. See, this is very important. Here we have taken the nature of signal as negative. And because we have taken the nature of signal as negative, feedback signal negative, we are getting positive sign in the denominator. If you see the final equation, C of s divided by R of s, it is going to be like G of s whole divided by 1 plus G of s into H of s. So this plus is very important. For negative feedback signal, we are going to get plus sign in the characteristic equation, and for positive feedback signal, we are supposed to get a minus sign in the characteristic equation. This is important. Same thing is mentioned over here. See, if you see the final output equation here, we are getting plus sign in the denominator. This is plus because we have considered that the system is equipped with negative feedback signal. That is important. In the same way, if we have a positive feedback signal, then we must get negative sign in the denominator polynomial expression. Finally, we conclude that if we have, say, minus plus, we must get plus minus at the end of the process. So this is very important. That means if we have a closed loop control system where G of s indicate the forward path gain, H of s indicate the feedback path gain, and suppose if you want to represent this entire system through a single block, that we can do. But the thing is that inside that block we need to write the representation of the parametric function via this particular equation, where we can write here as G of s whole divided by 1 plus minus G of s into H of s, where plus for negative feedback system and minus for positive feedback system. But in most of the cases we are considering negative feedback system. That's why characteristic equations are indicated by expression 1 plus G of s into H of s is equals to 0. This is very important. So this formula you have to remember. And while applying block diagram reduction technique, this will be one of the most important rule to reduced when we have this type of combination. That means one is the forward path, second one will be the feedback path. Forward path gain effective is G of s, feedback path gain effective is H of s, and suppose we want to represent that by a single block, then directly we can apply this formula. g of s upon 1 plus minus g of s into h of s to represent that particular system through a single block. That is important. So this is important. So negative, we need to take plus sign. For positive feedback, we need to take minus sign. That is important. So these expressions you have to remember. And then we started rules, which plays an important role in order to reduce the block diagram. Now, through these sets of rules, we are trying to convert block diagram into its equivalent parametric function, or you can say the gain of the system. For example, if we have the representation of the system in the form of, say, block diagram, and we want to convert that into its equivalent transfer function. So to convert block diagram into transfer function, we need to apply some rule. Those rules are called as block diagram reduction technique. The way we have done in case of signal flow graph. Suppose we have signal flow graph and we want to represent that into its equivalent transfer function. So we need to apply the concept of Mason's gain formula. In the same way, suppose we have a block diagram and we want to convert that into its equivalent transfer function. We need to apply the concept of block diagram reduction technique. So there are some 8 to 9 rules that we need to apply, that we need to first understand, and then depending upon the situation, depending upon the way blocks are connected in the system, we need to identify that whether we need to apply rule number 1, rule number 2, rule number 4, or rule number 8. So the first rule that we learn is, suppose if the blocks are connected in series connection. So first we need to identify that how we can make a comment that the blocks are connected in series configuration, because that is important. So the blocks are said to be in series connection when they are connected back to back. That is important. And second thing is that they do not have any summing point or takeoff point in between them. Just like the case I have shown over here. See, here we have three blocks: block number 1, block number 2, and block number 3. All the three blocks are connected back to back and they do not have either a summing point or a takeoff point in between them. That's why we can say that G1 of S, G2 of S, and G3 of S are connected in series configuration. Now suppose if you want to represent this combination by a single block like this, and to that block we are going to provide input like R of S, and we are trying to generate output like C of S. So what will be the parametric function that we need to write inside this block? And finally we conclude that when the blocks are connected in series, we need to multiply the gain of individual blocks. So in this, or inside this block, we need to write the product of G1 of S, then G2 of S, and then G3 of S. That is important. And this is going to be G of S. So this is very important. See, C of S related with R of S by the product G3 of S, G2 of S, and G1 of S. That is important. So finally, we conclude that when the blocks are connected in series combination, the resultant gain is simply the product of individual gain. That is important. So up to this particular point, we have discussed in the previous lecture. Now from this particular lecture onwards, we are also first going to discuss the remaining rules that plays an important role to reduce the block diagram representation for a system, and then if time permits we are also going to solve some numerical on block diagram reduction technique. So rule number 2, that deals with, suppose we have a blocks and suppose the blocks are connected in parallel configuration or parallel combination, then how to reduce them, that is important. Now this figure indicate that we have three blocks, like block number 1, then block number 2, and then block number 3, and all are connected in parallel configuration. Why they are connected in parallel configuration? Because the flow of signal in each block is in the same direction. For example, if you see that with respect to block 1, the flow of signal is from input to output like this. In the same way, with respect to block 2 of gain G2 of S, the flow of signal is from input to output. In the same way, with respect to block 3 of gain G3 of S, the flow of signal is from input to output. Hence, all the blocks are connected in parallel configuration. Then how to identify or how to uh, reduce this combination? Again, by a single block with input R of S and output going to be C of S. So what will be the function that we need to write inside this block? That is important. So how to identify that? So to identify that, first of all, we need to find out the outputs of individual block. For example, if you focus on block number 1 like this, so input to the block is R of S, gain is G1 of S. So what will be the output for this block? Output is nothing but input times gain. So it will be like x1 of S. So this is going to be input multiplied by gain. In the same way, output of block number 2 will be like input, which is nothing but R of S multiplied by gain. So it is going to be like R of S into G2 of S. In the same way, for block number 3, again we need to apply the same topology, like input is R of S multiplied by gain, which is nothing but G3 of S. So we are getting R of S times G3 of S. So this will be the output for third block. Now here we have connected a summing point, and I told you that summing point is basically used to add or subtract the signals which are coming in the form of input at that particular point. So with respect to this summing point, here we have three signal. First one is x1 of s, second one is x2 of s, and third one is x3 of s. So what we need to do, we need to find out the resultant of these three signals. So the resultant of these three signals will be like C of s is going to be x1 of s plus minus x2 of s plus minus x3 of s. Now what is x1 of s? X1 of s is nothing but r of s into g1 of s. In the same way, x2 of s is r of s into g2 of s, and x3 of s is r of s into g3 of s. So finally we conclude that if you see the relationship between output and input, when the blocks are connected in parallel configuration, simply we need to add or subtract the block gain depending upon the nature of signals coming at the summing point. That's why in general we have taken plus minus sign over here. So this will be the final output. So when the blocks are connected in parallel configuration, we need to add or subtract the gain depending upon the nature of signals coming as an input at the summing point. This is very important. So I want everybody to write down this because this is very important. The concluding statement is very important, that when we have blocks connected in series configuration, we need to multiply the gain of individual block. In the same way, when we have blocks connected in parallel configuration, the resultant gain is going to be the addition or the subtraction of the individual gain of each block. That is important. This will be a rule number 2. So take your time, write down this. I hope everyone is done with this. So finally we conclude that whenever the blocks are connected in parallel configuration, the resultant gain is going to be the addition or the subtraction of the individual block gain. That is very important, available at that summing point. If you have done with this, let us try to move and discuss rule number 3, and that deals with elimination of the feedback loop. This point we have already covered in our previous lecture, that suppose if we have a representation of a system in the form of this structure, like we have a forward path gain indicated by symbol g of s, we have a feedback path gain indicated by symbol h of s. With both the possible condition, we may have a negative feedback signal, we may have a positive feedback signal. And suppose if you want to reduce this entire structure by a single block, then how we are going to do that? It is simply the application of our previous load, that is nothing but g of s whole divided by 1 plus minus g of s into h of s. So this parametric function we need to place in a block, and to that block we need to apply some input in the form of r of s, and we are supposed to get output in the form of c of s. That is important. So if you apply that logic, we can directly write this. So this will be your rule number 3, elimination of the feedback loop. तो जब भी आपको सिस्टम में इस टाइप का स्ट्रक्चर मिलेगा, और अगर आपको लगता है कि आपको उसको एक सिंगल ब्लॉक से रिप्रेजेंट करना है, तो आप डायरेक्टली इसको इस फॉर्मूले में प्लेस्ड करके उसको रिप्लेस कर सकते हो. दैट इज important. This rule is called as elimination of feedback loop, and the derivation for this we have already learned in the previous lecture. Why we are getting this as an output, that is g of s upon 1 plus minus g of s into h of s. The thing is that you have to identify first, this is not the parallel configuration, this is a closed loop. Why? Because in forward path the flow of signal is from input to output, but in feedback the flow of signal is from output to input. So it is going to be a closed loop like this. That is important. It is not the two blocks connected in parallel configuration, because in parallel, if we have two or more than two blocks connected in that sense, that means the flow of signal through each block is going to be in the same direction. It may be from forward to backward, or it may be from backward to forward. That is important. So please note down this rule number 3, elimination of feedback loop. So if you have done with this, now let us move by solving a simple numerical based on the rule that we have learned so far on block diagram reduction technique. It is a very simple numerical, and the numerical is like, we have the representation of a system through a block diagram like this, and our objective is to find its transfer function, or we want to represent this entire system through a single block, and to that block we need to apply some input like r of s. We are going to get output in the form of c of s. So what will be the parametric function that we need to write inside this block, that we need to find out. Now, to solve numerical on block diagram reduction technique, first of all we need to identify that is there any possibility to apply rule number 1. That means first we need to identify that whether the blocks are connected in series. If they are connected in series, apply rule number 1 to club them and represent them by a single block. Then try to identify that is there any possibility to apply rule number 2, that means blocks are connected in parallel. If we came to know that blocks are connected in parallel, club them, represent them by a single block. In the same way, check is there any possibility to apply the concept of elimination of closed loop. If you identify, apply rule number 3, club them into a single block. So the thing is that in order to solve numerical on block diagram reduction technique, you need to implement the concept of observation technique. That means we need to observe very carefully whether the blocks are connected in series or in parallel, or is there any possibility to have the combination of blocks in closed loop. And once you identify that, apply rules to convert them into a single block and then move ahead. Now in this case, suppose if you observe here, this block of gain G1 of S and the block of gain G2 of S are connected in series. Why? Because they are connected back to back and they do not have any summing point or takeoff point in between them. So I can club these two block into series combination. And I know I told you that when the blocks are connected in series, we can represent these two blocks by a single block, and inside that block we need to write the product of individual block gain. So it is going to be like G1 of S into G2 of S. I hope that point is clear to everyone. So first you draw this structure, and here our objective is to find out the equivalent transfer function of this particular system using block diagram reduction technique based on the rule that we have learned so far in this particular topic. So first three rules we need to implement over here to find out the transfer function for this particular system. So we identify that G1 of S and G2 of S are connected in series configuration. So the modified system is given like this. So it is going to be like, now instead of mentioning two separate block, we have mentioned only one block. Now the gain is going to be like G1 of S into G2 of S. That is important. G1 of S multiplied by G2 of S. So this will be your forward path gain. Why? Because it is connected between input and output. So this is going to be G of S, that is G1 of S into G2 of S. Now let us try to observe that is there any possibility to apply rule number 2? No, it is not possible, because the forward path block and here this is what feedback path block, they are not connected in parallel configuration, because I told you that in parallel two or more than blocks are connected in parallel when the flow of signal is from input to output, or from output to input in all the blocks. That means the flow of signal will be in the same direction. But here we have one block in forward path and another block will be in the feedback path. So here we need to apply rule number 3, that means elimination of feedback path. So here the value of G of S is nothing but G1 of S into G2 of S, and the value of feedback path block is nothing but H of S. So if you apply elimination of feedback path or elimination of feedback loop over here, the sense of feedback signal is negative. So we can directly apply that logic like C of S divided by R of S is going to be like G of S whole divided by 1 plus G of S into H of S, where this G of S is going to be like g1 of s multiplied by g2 of s. That is important. So if you apply that logic, apply elimination of feedback loop, we can write here as g of s upon 1 plus g of s into h of s. Now this g of s we can represent like this, g1 of s into g2 of s. That is important. So in this way, the very complicated system we are now represented by a single block by applying certain rules of block diagram reduction technique. So whatever the parametric function we will get at the end of applying block diagram reduction technique, that means if we reduced a system into a single block, so whatever the function which we have obtained at the last of that particular process, this function is known as parametric parametric function of the system, or you can say transfer transfer function of the system transfer function of the system. That is important. So it is going to be like g1 of s into g2 of s whole divided by 1 plus, because negative feedback system, that's why we need to take plus, g1 of s into g2 of s. This indicates g of s multiplied by feedback path signal, that is nothing but h of s. So this indicates the transfer function of the system, which is nothing but c of s by r of s. So this is what a simple numerical through which we can understand what exactly block diagram reduction technique is and how we can apply those simple rules to find out the transfer function through BDRT rules. That is important. And this type of numericals were asked in GATE. The thing is that the complexity of the numericals are quite tedious, but ultimately you need to apply some sets of block diagram reduction rule to convert that system into its equivalent single block, and whatever the functions we are getting inside that block represent the parametric function of that system. That is important. So please note down this, and if you have done with this, now let us try to discuss some more rules which plays an important role in case of block diagram reduction technique to convert the complicated system into its equivalent single block. Now, rule number 4 deals with associate law for summing point. Now, what is the meaning of this? That means now in this case we are going to check whether it is possible to apply associate law for the summing point. That means if we have two or more than two summing points connected back to back, is there any possibility that we can switch or we can swap the positions of the summing point? Now, from rule number 4 onwards, we are trying to learn some more complicated rules which are very much essential in block diagram reduction techniques to solve the numerical and convert that into its equivalent single gain. So in this case, what we have done, we have taken two summing point, say S1 and S2, and to this particular system, we have taken some input and some output. To input to first summing point is R1 of S and R2 of S, and the output of this summing point is connected as one of the input to second summing point, and then we have one more input like R3 of S. And now in this case what we are going to do, first we will try to calculate what will be the output of this particular system, and then we are going to swap, we are going to interchange the position of these two summing point. Like instead of writing S1, now we will change the position of S1 by S2, and we will change the position of S2 by S1, and then we are again going to calculate what will be the output in that particular case. If output in first case and output in second case are going to match, then we can say that associate law is applicable for summing point. That means if we have summing points which are connected back to back without any takeoff point, without any block in between them, then it is possible to interchange their positions. So first we need to calculate the output in this case. So here the output of first summing point is R1 of s plus minus R2 of s, and the output of second summing point is going to be like input R1 of s plus minus R2 of s followed by third input signal, that is nothing but plus minus R3 of s. So this R1 of s plus minus R2 of s plus minus R3 of s will be the output of your entire system. Now what we are going to do, we will interchange the position of both the summing point. So instead of taking first, now we have taken second summing point, and then here we have connected the first summing point, and the input to the second summing point is nothing but R3 of s, so that we have taken over here, and the input to first summing point is R2 of s, that we have taken over here. Now again in this case we are trying to find out what will be the output in this case. So in this case, first the output of the second summing point will be a combination of R1 of s followed by R3 of s. So it is going to be like R1 of s plus minus, here we need to take plus minus R3 of s, and then the output of S1 will be like R1 of s plus minus, then plus minus R2 of s, and then plus minus R3 of s. See, the same logic is applicable over here. Now if you compare the output in first case and the output in second case, see the output in first case C of s is nothing but R1 of s plus minus R2 of s plus minus R3 of s. The same output, see the same output we are going to get in the second case when we have interchanged the position of summing points. So from this what we conclude? We conclude that associate law is applicable to summing point. The thing is that these 2 points must be connected directly. That means they do not have any takeoff point or any functional block in between them. Then it is possible to swap or interchange the position of summing point. So I want everybody to please note down this point. This is very important. And depending upon the structure given to us, we need to apply this logic. So you have to remember this. Whenever we are trying to apply block diagram reduction technique rule, the output of the system should not get changed. Before applying the BDRT rule, whatever the outputs the system is going to generate, the same output the system must generate after applying any rule of BDRT. It may be clubbing of summing points, it may be clubbing of blocks, it may be when they are connected in series configuration or they are connected in parallel configuration, or it may possible that when the blocks are connected in a closed loop. The thing is that before applying BDRT, if the system is generating some output, say A, the same output must be generated by the system after applying any rule of BDRT. If you are getting that same output after applying BDRT rule, that in that case the rule is correct and we can apply that rule for reduction purpose. So please note down these points. These are very important. So if you have done with this, let us try to understand this rule in some different way. That is there any possibility to split the summing point into two or three subpart? That means splitting of summing point. So suppose we have a system represented by this block diagram where we have a summing point, and at this summing point we have some input signal like R of S, followed by some auxiliary input signals like A of S. This may be a disturbed signal. Then we have a feedback signal B of S, and the output is nothing but the error signal, that is nothing but E of S. Now it is possible to split this summing point into two or more than two summing points. Yes, we can apply that logic too, because if we can interchange the position of the summing point, if they are connected directly back to back without any takeoff point or block in between them, then it is also possible to split a summing point. The thing is that while applying any rule of BDRT, I told you that output should not get changed. It will remain the same before applying that particular rule. So in this case, first of all, let us try to identify that what will be the output of this summing point previously without applying any rule. So here the output of summing point is error signal, and it is going to be like input plus auxiliary input minus feedback signal. So this will be the output of the summing point before applying any BDRT rule. Now, what we need to do, we are going to split this summing point. Suppose this is your first summing point. Now, this summing point we are going to split into two summing point, maybe say S1 dash or S2 dash. And if we get the same output after splitting, then we can say that, yeah, splitting is possible, or splitting a summing point is possible in case of block diagram technique. So we can split the summing point into two summing points. Like this will be your S1 dash and this will be your S2 dash. And again, the logic will remain the same. Now, in this case, suppose we are getting the same value of error signal, the value which we have obtained in the previous case before applying that rule, I can say that the rule is perfectly correct. So first we need to find the output of this summing point. So this will be like R of S plus A of S, and this is going to be input to second summing point. So this error signal is going to be like R of S plus A of S minus B of S. Now see, if you compare the value of this error signal with respect to this, both are nothing but same. That means it is possible for us to split the summing point. So please note down this. This is very important. Splitting of summing point. I hope this is clear to everyone that if we have a summing point it is possible to split that summing point into two or more than two summing point. That is important. Now, why we need to apply this logic, or why we need to apply this technique? Now, see here, suppose if you want to reduce this particular system to a single block, then here we can apply the concept of elimination of feedback loop if we split this summing point into two sub summing point. Now, this will be a clear picture of elimination of feedback loop. So we can redraw the structure like we having a summing point over here, and to this summing point we apply input r of s, followed by another auxiliary input a of s, and then here we are going to have a block, and then output of the block is going to be like c of s, and here we are having g of s upon 1 plus g of s into h of s. That is important. That is very very important. And then the input to the block will be like r of s plus a of s. This will be the main input that we have provided as an input to this block, and it is going to generate c of s as an output. That is important. So ultimately, you should know that associate law is applicable for summing point. That means if we have two or more than two summing points connected directly back to back without having any further block in between them or takeoff point in between them, then it is possible to apply associate law. Then it is possible to swap the position of the summing points. In the same way, if we have a single summing point, and if we think that if we split that summing point into two sub summing point, then we can apply the rule number 3 or rule number 2, then you can do that. The thing is that it depends upon the type of numerical given to you, but you have to remember that it is possible to apply associate law for summing point. It is possible to split summing point into two or more than two sub summing points. Now, let us try to understand what will happen if we change the position of summing point before block or after block. In the same way, suppose if we are having a takeoff point, and suppose if we change the position of takeoff point before a block or after a block, then how it is going to affect the behavior of the system. The thing is that whatever the rule which we are applying in BDRT, before applying the rule, if the system is generating some output, the same rule must be generated by the same system after applying that rule. Then only we can say that the rule is correct. So in rule number 5, we are going to discuss, suppose if we have a summing point, and if we shift that summing point before a block, that means suppose we have a system in which we have a block, and to that block we apply some input in the form of x, and it is going to generate some output in the form of y. Let us consider that the gain of that block is say a, and suppose here we are having a summing point like this, say s, and to this summing point we apply some input, maybe say y1, and now it is going to generate some output y star, that will be a combination of y and y1. Now suppose if we shift this summing point before a block like this over here, suppose we want to shift this, then is it possible to shift the summing point? Number one. Number two, if we shift a summing point before a block, what changes we need to maintain in the modified system so that output in both the cases, that means output before applying BDRT rule and output after applying BDRT rule, will remain the same? That we need to discuss. So suppose we have a system like this, where we have a block of gain G. To that block we apply some input in the form of R1 of S, and here we are having a summing point, say S, which is connected after a block, and to this summing point we have some more reference input signal like R2 of S, and now we are interested to shift this summing point before a block. That means we want to shift this particular summing point over here. So how we are going to do that? Now, before shifting a summing point, as I told you that first we need to calculate what will be the output of the existing system, and then we will shift a summing point before a block, and then we will calculate what will be the output in that particular system. And if the output are exactly matched, then we can say that yeah, it is possible. If the output is not matched, then we are trying to think that what additional efforts we need to take to match the output in the second case so that it will get exactly matched with the first case. That means अगर समिंग पॉइंट आप ब्लॉक के पहले शिफ्ट कर रहे हो तो वो केस में हम पहले आउटपुट कैलकुलेट करेंगे, और अगर वो आउटपुट हमारा एक्चुअल बेस केस के आउटपुट से मैच करता है तो कोई मॉडिफिकेशन की ज़रूरत नहीं है। लेकिन अगर मैच नहीं करता है तो वो केस में हमें सोचना पड़ेगा कि क्या फैक्टर है जो हमें ऐड करना पड़ेगा, या क्या मॉडिफिकेशन है जो हमें ऐड करने पड़ेंगे, जिसके कारण अगर हम समिंग पॉइंट ब्लॉक के पहले लेते हैं तो हमारा आउटपुट before applying that rule and after applying that rule both will be the same. That is important. So first we need to calculate output in this case. So output in this case is going to be like G into R1 of S plus R2 of S. I hope now this is clear to everyone why we got this output. See, first we need to calculate the value of this signal, which is nothing but the output of this block. So output of this block is nothing but input multiplied by gain. So input is R1 of S, gain is G. So I can write here as G times R1 of S. Now this G times R1 of S will be the input to the summing point, and here R2 of S will be the another input. So we need to club these two. So it will be like G times R1 of S plus R2 of S. Now it is very simple for you to identify and do the analysis. So the output of our actual system is this G times R1 of S plus R2 of S. Now let us try to shift the position of summing point before a block. Now see, in this case we have shifted the position of summing point before a block. Now here we have first summing point and then after that we are having a block. Now let us try to calculate what will be the output in this case. Again, to calculate the output, first we need to calculate the output of the summing point. So here's in case of summing point we have two signal. First one is R1 of S, second one will be the R2 of S. So addition of these two will be R1 of S plus R2 of S, and then that will be provided as an input to this particular block of gain say G. So the output will be input multiplied by gain. So I think in this case you will get output like G multiplied by R1 of S plus R2 of S. I hope this point is clear to everyone. So same thing is mentioned over here. See. So output is going to be like G into R1 of S plus G into R2 of S. Now let us try to compare this output with our actual base case. Now see, in actual base case we supposed to get the output like G into R1 of S. So here we are getting G into R1 of S. This portion is correct. And then we must get R2 of S. Now in this case we are getting R2 of S, but along with that we are also having one more parameter which is nothing but G, but we don't need to have this G in our output, and this G is going to multiply it with R2 of S. So where is R2? R2 is over here. So in order to match the output of both the cases, that means the output which we are getting after shifting a summing point before a block with respect to our previous case, we have an error, and the error is that we are getting additional parameter of G that is in multiplication with R2 of S signal. So to make the output in both the cases will be the same, what we need to do here, Suppose we add one block of gain exactly equals to 1 by g. So what will happen? We will get the same output which is required with respect to our base case. So what we need to do? We need to add a block of gain exactly equals to 1 by g. Now why we have taken 1 by g? Because we are getting g as an additional parameter that is going to be multiplied by our reference input signal, that is nothing but R2 of S. Now suppose if we placed a block of gain exactly equals to the inverse of this block gain, to which we have shifted a summing point before a block, and suppose we try to calculate the output in this case, so it is going to be the output of this block is going to be like R2 of S by G, because with respect to this particular block gain, input is R2, gain is 1 by G, so output is going to be equal to input times gain, so it is going to be R2 of S by G. Now this will be our one signal. Here we are having another signal, we need to add them, so it is going to be like R1 of S plus R2 of S whole divided by G. Now this is provided as an input to this particular gain. See, the same thing is mentioned over here. So if you try to calculate the output, it is going to be like C is going to be G multiplied by effective input, and the effective input is R1 of S times R2 of S by G. So GG will get cancelled, you will get this as an output. Now this is going to be the same with respect to our base case. See, previously we are getting G parameter which is going to be multiplied with respect to R2 of S, but the moment we placed a block in the path of R2 of S and the gain exactly equals to the inverse of the block gain to which we have shifted the summing point, we are getting the same output. So what we conclude? We conclude that if a summing point is shifted before a block, if a summing point is shifted before a block, we need to add inverse block gain at a summing point. This is very important. That means whenever a summing point is shifted before a block, we need to add inverse block gain. This is very important. And this you can remember by simply merging the initial alphabets of highlighted word. See, summing point initial is S, before initial is B, and inverse initial is I. So this SBI word you have to remember. Now what is SBI? SBI stand for whenever a summing point is shifted before a block, we need to add inverse block gain. जब भी आपके पास में समिंग पॉइंट रहेगा और वो समिंग पॉइंट अगर आप ब्लॉक के पहले ले जाओगे, तो हमेशा जिस ब्लॉक के पहले आपने उस समिंग पॉइंट को ले गया, वो ब्लॉक का जो भी गेन रहेगा उसका इन्वर्स आपको वो समिंग पॉइंट पे ऐड करना पड़ेगा. So SBI, if you remember, then you can easily apply this logic. SBI stand for when a summing point shifted before a block, we need to add inverse block gain. That is important. So I want everyone to please note down this point, because these points are very important and these rules are very important. That what will happen when a summing point is shifted before a block. Write down this final concluding statement. When a summing point is shifted before a block, we need to add inverse block gain. That is important. Take your time to analyze this particular logic, understand this, because whatever the rules which we are learning, they are very very critical rules, very important rules, which plays an important role to solve any numerical on BDRT. The thing is that this type of rules we need to implement very frequently while solving numerical on block diagram reduction technique, and this type of numericals are commonly asked in gate, maybe for electrical or maybe for electronics and communication engineering students. So you should know what will happen if you shift the summing point before a block. So SBI, you have to remember that whenever you shift a summing point before a block, you need to add inverse block gain. That's it. Now if you have done with this, let us try to move and learn some more rules on BDRT. Now suppose if you shift a summing point after a block, then what will happen? जैसा पहले अब आपने शिफ्ट किया है समिंग पॉइंट बिफोर अ ब्लॉक, तो हमने देखा कि जब भी आप समिंग पॉइंट को ब्लॉक के पहले शिफ्ट करोगे, आपको उस पर्टिकुलर ब्लॉक का जो इनवर्स ब्लॉक गेन है समिंग पॉइंट पे ऐड करना पड़ेगा, अगर आप वो रूल अप्लाई करना चाहते हो तो. इन द सेम वे, if you want to shift a summing point after a block, then what we need to do? Again, we need to take an example. So this is what the example we have taken over here. We have a summing point. To that summing point, we are having two signals, R1 of S, R2 of S, and the summing point is now available before a block. So first we need to calculate what will be the output in this case. So output in this case is like G into R1 of S plus G into R2 of S. I hope this is clear to everyone. Now it is very easy for you to understand how we are getting the output of the systems. Now what we need to do, we will shift the position of summing point after a block. See, now the block is available after, sorry, the summing point is available after a block. Now in this case, we need to find out what will be the output. So first we need to calculate the output of this block. It will be input multiplied by gain. So G into R1 of S. And now with respect to this particular summing point, we are having two signal. First is G R1 of S, second will be R2 of S. And suppose if you want to calculate the output will be the addition of two inputs. So G into R1 of S plus R2 of S. Now if you compare output in the previous case, we are getting G into R1 of S. So G into R1 of S is available over here. Now we need to get G into R2 of S. Now here we are only getting R2 of S. So G is missing. G is not available in this case. So what we need to do? Here we need to add a block of gain exactly equals to G, so that we can have the same output in both the cases. I told you that whenever you are applying any rule of PDRT, output before applying, output after applying that rule will remain the same. Then only we can say that the rule is correct. So in this case, the output, if you shift the block or if you shift the summing point after a block, is not exactly matching. There is a missing term, and the missing term is G. So here in this particular case, we add a block of gain exactly equals to G at the summing point. And then if you apply that logic, calculate the output in the intermediate stages and the output of the summing point, it will be like C of s is going to be g r1 of s plus g r2 of s. Now this is going to match with our base case. So what we conclude, finally we conclude that whenever we have a summing point and if we shift that summing point after a block, we need to add same block gain. This is very important. We need to add same block gain at the summing point. This is very important. So we have two rules which are related to the shifting of position of summing point. In first case, we try to shift the summing point before a block, and in that case, we conclude that we need to add inverse block gain. And in second case, we have shifted the summing point after a block, and we conclude that we need to add a same block gain at the summing point. So after these two rule, you have to remember only one rule. The second will be the complementary, or you can say exactly the ulta of first rule. So normally I remember the rule SBI. That means whenever you have a summing point and if you shift that summing point before a block, we need to add inverse block gain. So but obvious है, अगर आप summing point को आगे shift करोगे, that means after a block we need to add same block gain. So automatically वो याद हो जाएगा. So इनमें से कोई एक rule आपने याद करना है. तो normally I prefer SBI. So whenever you are shifting a summing point before a block, we need to add inverse block gain. So but obvious है उसका उल्टा, अगर आप summing point आगे shift करोगे तो आपको same block gain add करना पड़ेगा. That's it. So I want you to write down the explanation for this because this is very important. And if you understand this, why we are doing this, why we need to add inverse block gain, why we need to add same block gain, then it is very easy for you to solve any numerical on BDR. It may ask in GATE, it may be asked in IES, or if you prepare for any competitive exams, if you have a confidence that why this rule has to be maintained in that flow. That means if you know the basic fundamentals of, suppose if you shift a summing point before a block or summing point after a block, we need to maintain these things over here or there, then it is very easy for you to deal with BDRT rules. So take your time, note down these points because these points are very, very important. Shifting of summing point after a block. And finally, we conclude that whenever we are having a summing point and if we shift the summing point after a block, we need to add same block gain at the summing point. If you have done with this, now let us move and understand what will happen when we are shifting the position of takeoff point. Because I told you that in case of block diagram, we have two main points. First one is your summing point and second one will be the takeoff point. So in rule number 5 and rule number 6, we learn in detail about what will happen if you change the position of summing point, maybe after a block or maybe before a block. Now we are trying to understand that suppose if you shift the position of takeoff point before a block or after a block, then what changes we need to maintain in the system so that in both the cases we will get the same output. That is important. So the rule number 7, shifting of takeoff point before a block. So again, we need to take some cases. So here we have a system where we connect a block of gain G, and to that we apply some input R1 of S, and we have a summing takeoff point. Now this indicate the takeoff point. So takeoff point is this one, and through this takeoff point we have taken some signal for feedback purpose, and the signal is R2 of S. Now, in this case, first we calculate what will be the output of this feedback signal that we have taken for feedback purpose. So the output is C of S, and it is going to be like input multiplied by gain, that is input multiplied by gain. So see, this C of S is taken for feedback purpose. So the value of R2 of S is going to be like C of S, and it is going to be G times R1 of S. Now, in this case, what we need to do, we will shift the takeoff point before a block. That means now we are going to shift this takeoff point, and we will place that takeoff point over here before the block. Again, we need to apply the same rule or logic. That means whenever we shift the position of takeoff point before a block or after a block, the output or the intermediate output in the previous case, that means before applying that rule and after applying that rule, must remain the same. Then only it is possible to say that the rule is correct, or whatever the changes we have maintained in that particular shifting, they are nothing but correct. So if you shift the takeoff point before a block, then what will happen? Now see here, in this case, we have shifted the takeoff point before a block like this. Now the output and the input to the systems we need to calculate. Input is given to us, that is R1 of S, and here the takeoff point. So in this case, the feedback signal which we have taken from the takeoff point is R2 of S, and the value of this R2 of S is going to be R1 of S. Why? Because now the takeoff point is available over here. So the whatever the signal available in this path, the same signal we have taken for feedback purpose. So the signal available in this path is nothing but R1 of S. So R1 of S we have taken as an input for feedback purpose. So this is going to be R2 of S going to be equals to R1 of S. That's it. Now if you try to calculate the output, in this case the output is going to be like C of S is input multiplied by gain. So input is R1 of S multiplied by gain, that is nothing but G. That's it. Now if you compare the output with respect to the previous case, they are nothing but the same. See, C of S is nothing but G times R1 of S. See, C of S is nothing but G times R1 of S. So there will be no change in the output. But if you see the value of feedback signal, in previous case we are getting feedback signal value as G times R1 of S. Now here we are going to get only R1 of S. That means the factor G is missing over here. So what we need to do, in order to match output as well as intermediate output before and after applying the rule, in this case we need to add a block of gain exactly equals to G. That is important. I hope this point is clear to everyone. Take your time, note down these points, and if you apply this logic, you need to add a block of gain exactly equals to G in the path of feedback signal so that we can have the same value of feedback signal which we get in the previous case, G times R1 of S. So finally what we conclude that whenever we shift a takeoff point before a block, we need to add same block gain at takeoff point. That is important. So this point you have to remember. Then whenever we are trying to shift a takeoff point before a block, we need to add same block gain. But in case of summing point, the situation is exactly ulta or reverse, because SBI, when a summing point is shifted before a block, we need to add inverse block gain. But in case of takeoff point, whenever a takeoff point is shifted before a block, we need to add same block gain. That you have to remember. Again, I told you, I will tell you that how to remember this rule also. The way we define the remembering point in case of shifting of summing point, SBI. In the same way, in this case also, I have defined some logic to remember this rule also. But for time being, let us consider that whenever we are dealing with shifting of takeoff point, so takeoff point, when we shift before a block, we need to add same block gain. That is important. So please note down this point. This is very important. These rules are very important. So if you have done with this, now let us try to understand rule number 8. Now what will happen if you shift takeoff point after a block? Again, we need to take the same system. Like in this case, now we are having a block which is available after a takeoff point. That means takeoff point is available before a block. And now we are trying to shift this takeoff point after a block. Then what will happen? So first we need to calculate and analyze what are the values of output and feedback signal which we are getting in our base case. So here the value of feedback signal is R1 of S, because we have taken the feedback signal by tapping through this particular path, and the value of signal available on this path is R1 of S. That's why the value of feedback signal is R1 of S. And the output of the system or of the block is C of S, which is going to be G times R1 of S. So this will be the output for the system, and this will be the value of feedback signal. Now what will happen, or what we need to do? Now in this case, we are trying to shift the takeoff point after a block. Now again, we need to calculate the same output and intermediate values of the signal. Now if you calculate the value of output over here, it is going to be like this. See, output C of S is G times the input, or output is nothing but input times the gain. So input is R1 of S, gain is G. So output is going to be like G times R1 of S. And the same value of signal is available over the entire path. It may possible that you may tap the value of signal from this point, or from this point, or from this point. Now suppose we tap the value of the signal from this point, the value of feedback signal is R2 of S. Now in this case, this R2 of S is going to be exactly equals to G times R1 of S. Now see, if you compare the output before applying the rule and after applying the rule, they are nothing but the same. See, we are getting the output as G times R1 of S. Here again we are getting the output as G times R1 of S. But if you see the value of feedback signal, we must get the value of feedback signal as R1 of S. Now in this case we are getting the value of signal as G times R1 of S. So this G will be your additional parameter, which we don't want. This G we don't want, but it is available, or it is coming in the feedback path. So what we need to do? We need to remove this. So we need to add inverse block gain. That's it. So if you multiply this signal by 1 by G, so this G will get cancelled and you will get R1 of S, which will be the previous value of feedback signal. So finally we conclude that whenever we are going to shift a takeoff point after a block, we need to add inverse block gain. I hope this point is clear to everyone. It is very, very important. So, see, if you apply that logic, output will remain the same. That is nothing but G times R1 of S. Now, here we are going to tap the feedback signal from this particular point, and it is going to be like G times R1 of S, but we don't want this G. So what we need to do, we need to add inverse block gain in the path of feedback signal. So this GG will get cancelled and you will get R1 of S as an final value of feedback signal. That is important. So R2 of S is going to be like R1 of S. So how to remember this rule? Again, just club the initial letters of highlighted word. See, takeoff point when it is shifted after a block, we need to add inverse block gain, Thai. So in Marathi, normally we refer a sister like Thai. So by taking that word, it is very easy for us to remember this rule. Thai means whenever we are shifting a takeoff point after a block, we need to add inverse block gain. So if you remember this word, it is very easy to apply this rule. So in case of summing point, summing point, we have the rule SBI. That means whenever a summing point is shifted before a block, we need to add inverse block gain. In the same way, in case of takeoff point, we have maintained another rule that is nothing but tie. So what is tie? Tie is nothing but whenever a takeoff point is shifted after a block, we need to add inverse block gain. So if you remember these two rules, then it is very easy to apply any logic. For example, if the summing point is shifted before a block, we need to add inverse block gain. In the same way, if the summing point is shifted after a block, we need to add same block gain. Now, in this case, if you remember tie, that means whenever a takeoff point shifted after a block, we need to add inverse block gain. The reverse of that, whenever a takeoff point shifted before a block, we need to add same block gain. That is the way to remember these rules. This is my technique. If you follow, you can easily remember what will happen when a summing point is shifted before a block, after a block, or takeoff point shifted before a block or after a block. But it totally depends upon you how you can remember this rule. But the thing is that you have to remember this because these rules are very frequently applied in any numerical. As far as if you study the type of numerical that were asked in previous year gate, maybe for electrical or electronics and communication engineering students, in most of the cases either we need to apply shifting of summing point before a block or shifting of summing point after a block or takeoff point shifting before and after a block. So to apply that logic, you should know the fundamental aspect of these rules. So finally, we conclude that whenever a takeoff point is shifted after a block, we need to add inverse block gain. That is important. So I want you to please note down these points. These are very, very important points. Takeoff point, when it's shifted after a block, we need to add inverse block gain. Take your time, note down this. If you are done with this, now let us make a quick revision of these four rules. That means whenever we are having a summing point, and if we shift that summing point before a block, we need to add inverse block gain at summing point. In the same way, whenever we are having a summing point and if we shift that summing point after a block, we need to add same block gain. And then if we are dealing with shifting of takeoff point before a block, we need to add same block gain. And whenever a takeoff point is shifted after a block, we need to add inverse block gain. So here you need to remember SPI, and here you need to remember TI. That is important. So this table is the final conclusion that we have learned in the previous four BDRT rules, like rule number 5, 6, 7, 8. Please note down this. Then let us try to understand what will happen if we shift a takeoff point after a summing point. Now it is somewhat critical rules that we need to apply in very special cases. For example, if we have a takeoff point and suppose if you want to shift that takeoff point after a summing point, then what we need to apply. So first we will take a case where we are having a takeoff point which is available before a summing point. And first we need to analyze this situation very carefully. We need to identify that what will be the output we are getting um, at the end of that process. Then we are also need to find out what will be the value of feedback signal. And then if we shift the position of takeoff point after the summing point, again we need to apply the same logic and we need to find out whether we are getting the same value or not. If we are getting the same value, then it is very easy for us to conclude that yeah, it is possible to shift a takeoff point after a summing point. But if we are not getting the same value, then in that case, what additional steps we need to include or incorporate so that we will have the same value, that we need to decide. So first we will find out what will be the value of feedback signal and what will be the output in this particular case. So here the value of feedback signal is R1 of S. Now it is very easy for everyone to understand why we are getting feedback signal as R1 of S. And the output in this case will be input available over here, that is nothing but R1 of S, followed by one more input available over here which is nothing but Ys. So R1 of S plus Ys will be the output which is nothing but Cs. So output of the system is C of S, which is R1 of S plus Y of S, and the feedback signal which we are getting over here is R1 of S. This is very important. Now let us try to shift the position of takeoff point after a summing point. Now see here, we are shifted the position of takeoff point. Previously the takeoff point is available over here, and then we need to shift that takeoff point after a summing point. Again we need to apply the same logic. Let us try to calculate what will be the value of output and the value of feedback signal we are getting over here. So here the output will be like this, because this will be the output, and the output is nothing but the resultant of the input available at the summing point. So it will be like R1 of S plus Y of S. So this C of S is going to be like R1 of S plus Y of S. Now here we have a takeoff point, and through this point we are trying to get the value of feedback signal. which is nothing but R2 of s. So this R2 of s will remain the same, that is nothing but C of s, which is R1 of s plus Y of s. Now compare this value with respect to the previous case. So here output in first case is R1 of s plus Y of s. See, R1 of s plus Y of s. So we are getting the same output. So there is no issue with respect to output. Now let us try to compare the value of feedback signal we are getting in the previous case and in this case. Previously we are getting the value of feedback signal as R of s. Now in this case we are getting the value of feedback signal as R of s plus Y of s. So this plus Y of s we are getting as an additional signal. Additional signal. So what we need to do? We need to do something over here so that we will neglect or we will remove this additional added signal in the feedback path. So here we are getting additional signal of plus Y of s if we shift a takeoff point after a summing point. Now, is it possible to add one more signal over here of value exactly equal to Y of s but with negative sense? So they will cancel out each other and we will have only R1 of s as a feedback path element. So if you apply that logic, we need to modify the structure like this. Now see here, if you shift a takeoff point after a summing point, so we have shifted a takeoff point after a summing point. Now in this case, we are first calculated the value of output. So output is going to be like C of S, which will be the combination of R1 of S followed by Y of S, because here we are getting the signal like R1 of S plus Y of S. Now the same signal is available over here. Now this will be your feedback, but we want to remove this point, that is plus Y of S. So what we have done, we have put additional summing point over here, and to this summing point we add one more signal with a sense of negative. So the output of this summing point will be the combination of this input, which will be R1 of S plus Y of S, followed by this input, which will be minus Y of S. So these two will get cancelled out and you will get only R1 of S as an output. And this R1 of S will be your feedback signal, which we get in the previous case. So this arrangement we need to maintain if we want to shift a takeoff point after a summing point. It is very complicated. That's why I told you that rule number 9 and rule number 10 are complicated, applicable only in specific cases. Because the moment you apply these rule, instead of reducing the block diagram in the smaller version, we have created our complexity. That's why rule number 9 and 10 are critical rules, need to apply only in special cases. But you should know what will happen if a takeoff point is shifted after a summing point. So this is what the structure you will get as an output. So I want everybody to please note down this. What will happen if you shift a takeoff point after a summing point? See, the rule that we apply over here, and to validate that rule, the logic remains the same. That means whenever you are changing the position of any element available in block diagram, it may be say summing point, it may be say takeoff point, or it may be the changing of position between summing point and takeoff point. The rule is very simple, that before applying BDRT rule and after applying that rule, output and the value of feedback signal or the intermediate outputs will remain the same. If they are same, then we can say that the rule is correct. We can apply that logic in that system. That is important. So you have to remember this. So we are getting now the same value of feedback signal that we have supposed to get in the previous case, or previous case and this case values are nothing but the same. Now let us try to understand rule number 10, shifting of takeoff point before a summing point. In the previous case we learned that suppose if you shift a takeoff point after a summing point, then what will happen. Now in this case, we have a takeoff point which is available after a summing point, and our objective is to shift this takeoff point before a summing point. Then what will happen? Again, to analyze this, first we need to identify that what will be the output and feedback signal over here. So in this case, output of the system will be like R1 of S plus Y of S, and the same signal is available for feedback path because we have tapped the signal for feedback purpose from this particular path. Hence you will get the same value of feedback signal. So in this case, output and feedback signal are nothing but same, and that is nothing but R1 of S plus Y of S. Now what we can do, we will shift the position of takeoff point before a summing point. Now see, in this case we are having a takeoff point which is available before a summing point. Now let us try to calculate what will be the output and the value of feedback signal over here. In this case, the feedback signal is going to be like R2 of S, that will be equal to R1 of S. Now we supposed to get R1 of S plus Y of S, but here plus Y of S term is missing. See, we must get plus Y of S over here, but Y of S is missing over here. And if you compare the output, it will remain the same. See, output in this case will be C of S is nothing but R1 of S plus Y, R1 of S plus Y. Both are nothing but same. But if you compare the value of feedback signal, here the feedback signal is R1 of S plus Y of S, and here we are getting only R1 of S. So what we need to do? We need to add plus Y of S over here so that we will get the same feedback signal, which is nothing but R2 of S, which is going to be like R1 of S plus Y of S. That is important. So if you apply that logic, you will get the same value of feedback signal. See, the value of feedback signal over here is now exactly the same that we are expected to get before we shift the takeoff point before a summing point. So these are very complicated rules, but you should know how to apply these rules. That means what will happen when you shift a takeoff point after a summing point or before a summing point. So take your time, note down these points, make a quick revision on whatever the rules which we have learned so far in block diagram reduction technique. Rule number 1, rule number 2, 3, 4, 5, 6, 7 up to 10. Understand them, understand their physical significance, and if you have a comfortable zone with each and every rule, then we are going to start numerical on block diagram reduction technique. That is very important. So let us make a quick revision of what topics we have learned so far. So far we have discussed rule number 1 that deals with when the blocks are connected in series. So finally we conclude that whenever the blocks are connected in series, we need to find the resultant by multiplying the gain of individual block. or the resultant gain will be the product of individual block gain. In the same way, when blocks are connected in parallel configuration, the resultant block gain will be the addition or subtraction of the individual block gain. Then we understand the concept of elimination of feedback loop. So this is very important. Whenever we are having a closed feedback loop, we can apply this rule directly, like g of s upon 1 plus minus g of s into h of s. And then rule number 4 deals with associate law applicable for summing point. Yes, it is possible to shift the positions of two or more than two summing points if they are connected directly without having any block or takeoff point in between them. Then we also discussed how to split summing point. And then rule number 5, 6, 7, 8 deals with the concept of shifting or summing point before a block. And we conclude that whenever we shift a summing point before a block, we need to add inverse block gain, then shifting or summing point after a block. And we conclude that whenever we shift a summing point after a block, we need to add same block gain. Then we discussed in detail about what will happen if we shift a takeoff point before a block. We need to add same block gain. And then when we shift a takeoff point after a block, we need to add inverse block gain. So this table you have to remember. And finally, we discuss some critical rules that plays an important role if you shift a takeoff point after a summing point, what we need to do, and if you shift a takeoff point before a summing point, what we need to do. So these points are very important. And once you understood this, now let's try to solve numerical on block diagram reduction technique. Now these numericals are normally asked in GATE, but for solving this numerical, this theory is very important. So first numerical on block diagram reduction technique is determine the transfer function of a system represented by a following block diagram. So here we have some block diagram, and our objective is to find its transfer function using block diagram reduction technique. So how to solve this numerical? Again, I told you that in order to solve numerical on block diagram reduction technique, you have to remember those rules which we learned in the previous case, and by observation you need to identify that which rule we need to apply first. It is not at all necessary that there will be a thumb rule कि पहले आपने first ही करना है, then second, then third and fourth. ऐसा कुछ नहीं है. The thing is that you need to observe very carefully the diagram given to you, and then based on the logic, if you identify that these two blocks are connected in series, club them, reduce them into a single block, then identify whether they are connected in parallel, club them, represent them by a single block, and then identify whether you are having elimination of loops or not. Then identify that is it possible to shift the position of summing point before block, after a block, or position of takeoff point before block, after block, so that we can apply some logic. So the ultimate objective is to convert this complicated system into a single block like this, to which the gain is going to be like r of s. The input to the gain is r of s, and the output is going to be c of s, or in this case it is nothing but y of s. So what will be there inside this function, or what will be there inside this block? That question mark indicate the transfer function for this particular system. That's it. That is very important. So if you apply that logic, first we need to understand that in this case this indicate the input, and this y of s indicate the output, and our objective is to convert this particular system like this: input to output, and here we need to have some parametric function that indicate the gain of the system. So first we will observe that is it possible to have a combination of blocks which are connected in series configuration. Now see, if you observe these two blocks, G1 and G2, these two blocks are connected in series configuration. Why? Because they are connected back to back and they do not have any summing point or takeoff point in between them. So we can treat these two blocks as a combination of two blocks connected in series configuration. So we can club them by G1 into G2, because I told you that when the blocks are connected in series, the effective block gain will be the product of individual block gain. In the same way, if you see these two block, these two block, that means block of gain G3 and block of gain G4. Now these two are in parallel, so we need to club them. Why they are in parallel? Because the flow of signal in both the blocks are in the same direction from input to output. See, input to output. That's why these two blocks are in parallel, because at one point we have takeoff and one point we have a summing. So we need to club them, and we can club them by G3 plus G4. Why? Because when the blocks are connected in parallel, we need to find the equivalent gain by adding or subtracting their individual block. Now in both the cases the gain are positive, that's why G3 plus G4. So the rule are, first observe, is there any possibility of having series combination? If not, then check, is there any possibility to have parallel combination? If not, then check, is there any possibility to apply elimination of feedback path? If not, then apply rule number 5678. That means, is it possible to shift takeoff point before a block? Is it possible to shift takeoff point after a block? But the thing is that which rule we need to implement, that again depends upon, if you shift a summing point before a block, then what will be the reduced version available with us? Based on that, we need to think whether we need to shift summing point before a block or after a block. So let us try to analyze this. So here, if you solve G1, G2 in series and G3, G4 in parallel, the system is going to be like this. I hope this is clear to everyone. So here previously G1 and G2 are in series. Now we apply rule number 1 and club them into a single block of gain G1 into G2. And here we have two blocks connected in parallel. We apply rule number 2 to convert them and represent them by this expression like G3 plus G4. Now, if you see this particular path, here we can apply the elimination of feedback path. Why? Because this will be the forward path of gain G1 into G2. This will be the feedback path of gain H1. And here we can easily apply elimination of closed loop. I hope this point is clear to everyone. So by applying elimination of closed loop between G1, G2 followed by H1, the modified diagram is something like this. I hope this point is clear to everyone. Now, if you understood this, G1 into G2 whole divided by 1 plus G1 into G2 into H1. Why we have written this? Because in this case, see, the value of G of S is nothing but G1 into G2. The value of H of S is nothing but H1. So elimination rule is G of S upon 1 plus. Why we have taken plus? Because see, the nature of feedback signal is minus. That's why plus. So 1 plus G of S into H of S. So this is going to be like G1 G2 whole divided by 1 plus G1 G2 into H1. So same logic is applicable over here. Now what we need to do? Now here we need to identify that is there any possibility of blocks in series, or you can say block in parallel, or elimination of feedback loop. That is important. Now this block and this block are not in series. Why? Because they have a takeoff point in between them. In the same way, this block and this block are not in series because they have a summing point in between them. So it is not possible to uh, have the flexibility to apply rule number 1, 2, or even 3. Now in this case, we need to apply rule number 5, 6, 7, or 4, 5, 6, 7, like shifting of summing point or takeoff point before or after a block. Now we can do, we can shift this summing point before a block like this, or it may possible that we are going to shift this particular takeoff point after a block. We have two possibilities: either shift this summing point before a block and apply the rule SBI, shifting of summing point before a block, we need to add inverse block gain at the summing point. So here we need to add a block of gain exactly equal to inverse of this particular value. Or if you shift this takeoff point after a block, apply the rule TAI. So if you shift this takeoff point after a block, we need to add inverse block gain. So here we need to add block of gain exactly equals to 1 upon G5. So in this case, I have applied a rule that whenever we shift a takeoff point after a block of gain G5, we need to add inverse block gain. So modified version is something like this. So in this case, what I have done, I have shifted this takeoff point after a block and apply the rule tie. Whenever a takeoff point shifted after a block, we need to add inverse block gain. So gain is G5, so inverse will be 1 upon G5. That is important. So it will be like H2 by G5. I hope this point is clear to everyone. Please note down and understand these steps very carefully because it is very important. So once you have done with this, now what we need to do? Uh, Again, apply the same logic. Is it possible to have a pair of series combination of blocks or parallel combination of block or elimination of feedback loop? Now see, in this case, this block and this block are connected in series configuration. So we can club them and find out their equivalent block gain. So by solving G3 plus G4 followed by G5 in series combination, the modified block diagram is given like this. So here we have clubbed them and find out their resultant, that twin series combination. So G3 plus G4 multiplied by G5. Now if you observe this particular portion, we can apply elimination of feedback path, because this is the forward path, this will be the feedback path. So we can easily apply elimination of feedback loop over here. So here in this case, G of S is going to be like G3 plus G4 multiplied by G5, and H of S in this case is going to be like H3. So if you apply elimination of feedback path over here, we can easily find out the modified block diagram for the numerical. So it will be like this, where G of S is G3 plus G4 into G5 and H of S will be H3. Now it is very easy to find out the reduced version of this system. Now see, this block and this block are connected in series. So what we need to do? We need to multiply the gain of individual block to find out their resultant, and then apply elimination of feedback loop. So it will be something like this. Now see, this will be the forward path of gain G of S, and the value of G of S will be the entire term available over here, and H of S will be the feedback path gain, which is nothing but H2 by G5. Now we can apply elimination of feedback loop. Now see, the feedback path signal is positive. So here we need to take g of s whole divided by 1 minus g of s into h of s. That's it. Where g of s will be this entire term available inside the block, and h of s will be h2 by g5. So if you apply elimination of closed loop over here, you will get this as an answer. So whatever the parametric function available inside this single block, this represent the transfer function of this particular system. And a very complicated system which we have represented in the form of block diagram, that we are reduced into a single block. Now see, here we have only one block. Input to that block is r of s, output of the block is y of s, and whatever the function which we have written over here, this indicate the transfer function of this particular system. So this is what the significance of block diagram reduction technique. And in this way, we are in a position to find out the transfer function of a system if block diagram of the system is known to us. In the next lecture, we are going to solve some more numerical on BDRT. You can take this as an homework, numerical number 2. Again, in this case, our objective is to find the transfer function of the system using block diagram reduction technique. We will start our next lecture by solving this particular numerical, and then we will solve some more numerical. In the next lecture, we are also going to solve a numerical in which signal flow graph is known to us. Our objective is to solve signal flow graph by using block diagram reduction technique. That means first we will convert signal flow graph into equivalent block diagram, and then apply BDRT rule to find its transfer function. So till then, revise whatever the topics we have discussed in today's lecture, because these rules are very important. If you want to gain confidence on solving numerical on BDRT, you have to remember those rules. Thank you.